your chairman during this morning session. We will start now, but I have to ask one question. We would like to record your talks and your presentation. If someone doesn't like that or doesn't agree with that, please tell us now. Thank you. And now we can proceed with our first lecture, with our first presentation. Our first presenter is Dr. Goran Damjanovic from the Astronomical Observatory Belgrade with his lecture towards Gaia DR3 and some results of comparison between Gaia DR2 and ground-based data. Dr. Goran Damjanovic, the floor is yours. Thank you. You can start.
Okay, thank you. Good morning. I'm going to talk about next Gaia solution, third data release, and about some results of the comparison between second Gaia solution and ground-based data. At the beginning, just to speak a little about the first satellite Hipparcos catalog of European Space Agency at the end of the last century. It was the big project. Gaia is the second one of ESA mission, and that observation period covered less than 4 years. You can see here. Before that, it was FK4 and FK5 dynamical catalogs, and the Hipparcos is the first kinematic catalog connected in the optical domain, connected to ICRF system based on the VLBI radio observations of a very long baseline interferometry method. That method started at 1980 and the good data 85. And ICRF at that time, there are about 700 radio objects with very precise coordinates collected with that very precise VLBI method. And first of all, that Hipparcos catalog is based on the middle. The epoch of the catalog is the middle of that observation period, and with about 120,000 stars, the FK5 list has got about 1.5 thousand stars, plus some few thousand stars of faint stars at that time. And Tycho catalog with about 1 million stars, Tycho second with 2.5 million stars. But the best positions, proper motions in both positions and the parallax are in Hipparcos catalog. After that, it was the problem with the first parallaxes with the errors. Also, some amount of stars have got parallaxes with minus, which is not correct, of course, not possible. And Van Loven did a new reduction of at Cambridge of raw Hipparcos data, and now it's Hipparcos second or a new reduction of raw Hipparcos data. It was a book about it, and a new catalog with beta positions, proper motions, and better results for parallaxes. It's the base of that catalog, 5 parameter solution for each star. Gaia launched at the end of 2013, and it's the second big satellite project of European Space Agency. And it started to collect data to do observations at mid of 2014. Mostly in astrometry, 5 parameter solution for each star, coordinate is proper motion and parallax, and photometry. At the beginning, it was the goal to catch about 1 billion sources in astrometry and photometry until 20 magnitude in the P band and about 150 million objects until 16 magnitude about spectroscopy. As we can see later, in the second release, there are near double of that predicted sources. And in the future, it's the plan to establish a new reference frame in optical domain, Gaia celestial reference frame connected to ICRF. Gaia is doing in optical domain. ICRF is based on the radio domain. It means it's necessary to link that to coordinate systems, and because of it, it's necessary to have some objects for good connection in line with that predicted error, and the quasars based next to Gaia CRF is playing in the future, especially for quasars visible in both optical and radio. And it's for objects, sources fainter than about 16, 17 G magnitude. In line with that Gaia mission, at that time, about 2013, to do some jobs at our observatory in line with that very important European project. We established the Serbian-Bulgarian mini network telescopes to use our, at that time, just one 60 centimeter telescope at Vidovica and a few other telescopes in Bulgaria at Belgradček, 60 centimeter, and 3 telescopes at Rožen Observatory, mostly 2-meter Rožen telescope. And during that, from that time until now, during that period, there are 3 joint research projects between Academy of Sciences of Serbia and Bulgaria. And you can see each one is during 3 years. You can see that 3 projects here. Also, at our observatory, there are 2 PhD students to do investigations about photometry and morphology of that quasars visible in both optical and radio, important for mentioned link. Miljana Jovanović and Gabriela Marković. Miljana Jovanović about photometry, and then Gabriela about morphology investigation of mentioned objects. About solutions until now, we've got first and second data release of Gaia data. First published in September 2016, and the next one in April 2018. First one is based on the 40 mounts, a little bit more than 1 year, with 2 million stars, and it's not independent one because it was necessary to use Hipparcos data to produce proper motions with good accuracy. Because of it, it's a type of Gaia astrometric solution at the epoch of catalog to 2015. And second data release of the Gaia observations based on 22 mounts with 1.3 billion stars. As you remember, the goal at the beginning, it was just 1 billion. And plus 0.4 billion fenced sources, just with coordinates. The main list, about 1.3 billion stars, is based on a 5-parameter astrometry solution, positions, proper motions, both coordinates and parallaxes. In line with that, it was one paper published 2 years ago with few colleges, in cooperation with few colleges from Paris Observatory. And also we did some efforts in Gaia Alerts observations using that mentioned Serbia-Bulgaria mini network telescopes. And during last 6 years, from October 2014 until now, we did about 80, 90 objects, about 15 per year. And the Gaia Alerts produce about 4,000 alerts per year during last few years. Our intention and the main instruments and plans about that Gaia Alerts task is published in this paper 2014 in our Serbian Astrometry Journal. Here you can see about the list of files. The domain list is here with 1.7 billion objects, as I mentioned a few minutes ago, 1.3 with all 5 parameters and 0.4 for just coordinates. And other files about Cepheid, error, Lyre, and other informations. Just to put your attention on the data, here you can see coordinates with errors, coordinates in degrees, errors in milliseconds per year, milliseconds, and proper motions also milliseconds per year, parallax and proper motions in parallax in milliseconds, and proper motions in milliseconds per year. Parallax could be with minus. It's necessary to take care about it. I asked some people about that problem because it was the same problem in Hipparcos catalog, but told me that it's a result after solution of that 5-parameter necessary to input all calculated data. Maybe it's better to be empty or maybe or just 0, but it's not of importance that minus value. Told me that they are putting in that columns calculated values, and also that minus something value. Here you can see G magnitude also in near blue and near green bands, two values of magnitudes. About the next release, it's divided into early third solution and third solution. And the first one is going to appear at the end of this year with improving the astrometry positions, parallax and proper motions in both coordinates for about 1.5 billion stars. And plus 0.3 billion stars just for coordinate. It's photometry between 3 and 21 G magnitude for 1.8 billion stars, all mentioned stars. And also that photometry near blue and red part of visible domain for 1.5 billion stars. Also 1.5 million objects are going to use for Gaia CRF in the future. And third Gaia data release is going to publish at during the second half of 2022. And in that release, it will be early, third data release with mean radial velocities for stars, object classification, some astrophysical parameters about spectroscopy, photometry of the objects, about parabolic stars classification, with epoch and results, and some information about solar system results as orbital solutions and individual epoch observations, etc. Also, some results about quasars and extended objects, and about double multiple stars. Also, there is a list of Gaia astrometry photometry survey data for objects about 505 degrees around Andromeda galaxy, etc. It will be based on about 34 months for that period of Gaia observations at that 2016 epoch of the catalog based on the ICRS International Stellar Reference System and in line with the barycentric coordinate time. Here you can see domain list of mentioned information, and it's just important to note that the photometry system for mentioned bands is different from the photometric system which is used for first and second Gaia release. And here you can see about numbers for the right column for the first, middle, second, and for the next early third data release. You can see the numbers about 5 parameter solutions for some number of sources, 2 parameter, etc. About G magnitude, about photometry near the red, near the blue part of the optical domain, radio velocities, etc. About a comparison of Gaia data and some other catalog, it's very difficult to do. And here I used my own catalogs based in line with my PhD, based on ILS International Latitude Service data, 7 stations on the same near the same latitude, observed the same stars during 80 years, near 1 century, and it's very important for very precise proper motion in declination, because it's zenith telescope data. And also the 7 stations, 7 instruments. Also, I used 7 independent latitude stations. Between them, it's Belgrade material, Belgrade, Varšava, Pulkovo, Poltava, Belgrade, Irkutsk, Blagoveshchensk, etc. And 10 PZT photographic zenith tube instruments, Misuzawa, Washington, Richmond, Ongeyo, etc. First of all, I wanted to compare ILS proper motion in declination, and realize it in line with the second data Gaia release that about right ascension in x-axis, there is some sinusoidal curve in line with difference of that mentioning the proper motions in declinations between ILS and second data Gaia release. It's white cycles here. And points are about 400 information for differences for near 400 stars of that ILS catalog. And after removing that sinusoidal curve, black rectangles are the same as cycles, but without that effect, that sinusoidal curve. And first of all, I was realized one paper in astronomy, astrophysics with Paris last year, because I was thinking that it's because of its source is double stars. But after that, after Lindgren results about inferior astrometry for Gaia stars, bright part of Gaia stars until 6G magnitude. Also that some indication that there is a rotation of the bright part of Gaia catalog, the second data release, until 13G magnitude. That amount of stars have got some rotation around the second part of Gaia catalog, fainter than 16, 17 magnitude, G magnitude, because that second part is connected to quasars, but quasars are not visible for that bright part, and because of it, that bright part is with not so good astrometry as the faint part, also not connected directly to quasars as a faint part of that catalog. And that rotation, there are three parameters in the X, Y, and Z. Y1 is significant at the 2 sigma level, which is of the order of 0.1 milliseconds per year. And I realized that I've got, using my data, the same level of rotation. Also, here up, you can see in this image about ILS and the Hipparcos, ILS and new Hipparcos, also Hipparcos, second data release, the same behavior as previous, picture. Here down in this picture, you can see distribution of differences, solid line, ILS minus second Gaia data release differences in proper motion and declination, and residuals with another line, dashed line of that near 400 ILS stars. To do that verification, you can see that ILS catalog is very good, with good accuracy, close to second data release Gaia accuracy, and better than Hipparcos and new Hipparcos, because ILS stars is with 0.21 mean accuracy of that in proper motion declination of that stars. For the same stars, Gaia 0.14, 0.58 for Hipparcos, 0.36 for new Hipparcos. For verification of that result, F-test was used, and supported that result. To reject some stars, I applied 3 sigma criterion, and also method Tukey's fences. Okay, and to check standard normal distribution, Shapiro-Wilk test. And here you can see about the spin. I calculated omega y as because it's a 2 sigma significant result. You can see about differences, calculated free term omega y, omega x, omega y using a least square method. It's one catalog, another catalog. Lindegren during this year in astrometry physics published a paper about it. And in this table 1, you can see the last column about minus 0.64 ILS minus second data Gaia release, about minus 0.2 between ILS and new Hipparcos. Between Hipparcos and the Gaia, minus 0.4. Anyway, here also the same for independent lattice stations. And about all ILS independent lattice stations plus photographic zenith tube stars, you can see the same results. After applying some rejection criterion for some less amount of stars, you can see just maybe about 20% less value that this one 0.6 minus 0.6 here is minus 0.5. Anyway, that Lindegren indication is supported with my data in my results here, and we published that ILS results last year with Taris and in astronomy physics. Okay, and during this year in astrometry Hechten. And just to mention that during the end of this year, it's going to appear earlier data, third Gaia data release. After 2 years after that, third data release complete based on photometry morphology and other data. Our part here is also to investigate photometry morphology or phasers useful for that mentioned link. And about second part, we support that Lindegren result that bright Gaia second data release is with inferior astrometry. Also about result in spin in omega y ATD order about 0.1 milliseconds per year. And it's more or less the all about it. Thank you.
Thank you, Dr. Goran Damjanovic. I open floor now for the questions and also for the comments. Please ask your question, simply unmute your microphone, or if you want, write the question in the chat box. There is any question or comment? Do you hear me?
All is fine, Ivana. We can hear you.
Yes, okay, that's fine. That is important to hear me.
Yes.
If not questions, I suggest to continue in the same manner with the next presenter. Once again, thank you, Dr. Goran Damjanovic, for your presentation and talk. Now, we move on to Dr. Anatoly Ivansov with his presentation, Adapting Image Centroiding to Astrometric Differential Reduction. Please, do you hear me, Dr.?
Yeah. Okay. Good morning. Yeah, okay. Now I can share the screen.
Okay, you can start.
Good morning, dear colleagues. Yes, good morning, dear colleagues. I'm glad to share some results of the work that we started in Turkey in astrometry of asteroids. So I would like to talk about image centroiding and in fact image processing, its role on the errors that we get in astrometric reduction. So I will talk a bit about instrumentation and some numerical results that we got for now. And I would like to start with minor planet center statistics with respect to ground-based astrometry. I have pre-selected the codes of the stations that have standard error standard error less than 1/10 of arc second. And you can observe that in the, let me say, past even 40 years, there are not too many observatories that can produce astrometric measurements of high accuracy. You see, I have put also the column with a number of positions that were submitted to the minor planet center. And I have removed those stations that produced less than 10 positions with this sigma, as I consider that if you get 2 or 3, let me say, positions and calculate sigma using them, we cannot think that they are quite reliable. And of course, 10 is also not the limit for or the starting, the lower bound for reliability. But of course, I would like to say that it is better to look at the observatory codes that produced many images with quite good astrometry. The code 244 is related to occultation observations. So this is completely different method of observations, and you see, yes, they produce quite good accuracy. But the rest of observations, they are usual observations that are done with direct imaging. And I would like to emphasize that the number of observations available now at the Minor Planet Center is about 277 million. And of course, the Gaia positions will be very important for improving orbits of the asteroids. But considering the time length of Gaia mission, after it, we will meet the situation that the orbits of asteroids and also other solar system bodies will deteriorate with time, and we will need to do and to continue ground-based observations. And of course, it is very important, even if we have access to space observations of asteroids, to keep the best or the smallest standard error of astrometric observations for the solar system objects, as far as they are moving quite fast. So I will try to put your attention to only one factor that is related to to the measurements astrometric. This is centroid. And of course, it was the the first works related to digital centroiding algorithm started in 1975. I have extracted on the 3 first papers, but of course this time the amount is growing. However, the methods of calculating the centroid of the image are really not growing in number, unfortunately. And the first works, the first papers were discussing centroiding digital image processing with respect to photographic data, and with using special devices. Of course, not CCD imaging, but also the measurements that we can use for numerical processing. I would like to say that most of methods that we use today are described in these 3 papers. So I will make just a list of these, let me say, algorithms that are used even today. So most of them are based on the radial symmetry, and I have listed only those here. So if we consider projection of the 2-dimensional image profile on one of the axes, we can introduce this function m that is obtained while we do summation along another variable. So if we put here, for example, y, then we need to make summation over x. It's just a simple approach for doing calculations and nothing more, really. Of course, the symmetric Gaussian function is very popular even today, and such software like, for example, Astrometrica and other codes, they are using it widely. B means background, sky background. Ash is related to the total intensity. And X with lower index C means the position in the X coordinate. Sigma is the usual width parameter used for describing Gaussian function. Of course, it is related to the full width at half maximum. The moment method is, sorry, I have forgotten to tell that the pixel values are fitted with these constants B, H, XC, and sigma, and we determine the position in each coordinate using this kind of non-linear least squares, for example, fitting. The moment method is quite easy, and it is based on as well on the background, and it does not require any fitting. So it was probably the most popular method in the past, before people realized that background can seriously, significantly change the position of the centroid. So there was introduced modified moment, where you can see you can establish a threshold for the pixel values and neglect, for example, those that values in the image processing that are below this, for example, threshold value. This is very popular method even for today. For example, for comet methods measurements, when you can discard, for example, all pixels that are out of some aperture radius. The median method, I have not put formula, but I consider that it, I mean, all people know that it's just a statistical median for calculating the median as a centroid of the image. It was popular for faint image centroid. However, there is a trouble that as soon as you have an image of a faint star, its peak can be, it is located within 1 pixel, and the neighborhood with respect to this pixel can be completely in the background. And so you can use even just usual search for the bright pixel, and of course the astrometric measurements will be limited by the size of that pixel. Okay, half of diagonal of it. And the derivative search, when you can calculate the derivative or slope of the profile, and you using the values of pixels, so for example this marginal function at different points. Unfortunately, this formula is traveling with a printing mistake, a typo, when this coefficient is missed, and each component that is taken in the bracket, it is a central approximation for the using Lagrange formula for the derivative. And of course, if you have different central approximations for the same quantity, you should take 1/2. And unfortunately, this is not the best choice for using these values. And in mathematics, you can take as, for example, one additional x plus 1, x minus 1, x plus 2, x minus 2. You can take at m at x, m from x, and you get the fourth order of approximation instead of this formula that keeps on the second order. And combination of second order just gives the usual second order. So sorry, I would suggest that it is sometimes we need to check the formulas. And of course, I have put 3 points. It means that there is a big variation of methods that can be introduced. What are the problems of these methods? It was discovered by experimenting with modeling image profiles and calculating the centroids. First of all, it is irregularity of sky background. And of course, as I've mentioned, for the fine stellar images is a complete problem. In other words, if you have many stars and you have measured their positions, and these faint stars are present as one pixel, you are destroying your calculations, least squares calculations, and perhaps it is the better way is to reject the bad measurements from ordinary for example, image fitting instead of using them, especially as we know the number of faint stars are quite big, so we can destroy really the good measurements that we can achieve in this way. The second problem is lack of radial symmetry for the stellar profiles. And evidently it can be caused, as I've written here, by optical aberrations or charge transfer inefficiency. This approximation that is using elliptical Gaussian function was used by Chio in one of the first works, and it has been shown that it is much better than usual spherical radial symmetry Gaussian. And of course, I have to point your attention to one problem that has not got solution, and it has to be introduced through algorithms. This is multiplicity of the object. For example, if you are determining centroid of a star, and in fact the star is a wide double star that is on the ridge of resolution, of course you can discover perhaps its two components. And what will do the centroid algorithm, it depends on the algorithm parameters itself. And of course, it's not only the problem of the object itself, but it can be related to just overlapping of image profiles. In other words, if we observe, for example, two different and quite wide separated objects, I've got in
5 minutes.
Okay, or get them, let me say, separate with a small telescope. Perhaps we will get them quite close and we will meet this problem. So I will just say a few words about the telescopes that we use in the south of Turkey. This is a telescope that belongs to our university, 60 centimeters, and it is the telescope that I will show the results from it. And there are a few telescopes that are located on the mountain top, 2.5 kilometers close to Antalya. I would like to show its photo and to show its scale. So it is about 0.7 arc seconds. So, what we have done, we suggest to obtain several images in a series and calculate the standard deviation of each star that we have while we get different images. So let me say, in other words, we calculate the group, we find the same stars on each image, then find the centroid of this group of stars, remove motion of centroid from image to image, I mean the motion of the telescope, because it is not, of course, perfect. And then we calculate the mean position of the star within this centroid and calculate standard deviation. And this standard deviation we can consider as the measurement error. So I would like to plot the points that are related to the series of 46 images. So if you, here are red and blue, they are related to the measurements done for the same series, but with a bit different image processing parameters. That was signal to noise ratio detection and aperture radius. And you can see, for example, that there are measurements that are blue and that are better than the measurements represented by red dots. It looks the difference is quite small, but I would like to remind that it is based on the 46 images. So each point is determined quite well. And of course, we can calculate the general sigma that for each star. And we can see even here that the blue stars are, blue points are located close to the origin. And it means that, for example, by changing image parameters, we can improve our astrometric measurements. And of course, you will have some byproduct, like the motion of the telescope. This is the motion of these centroids that you can use. I mean, these slopes for calculating how good the polar axis of the instrument is aligned to the celestial pole. And let me come to the conclusions. So the first point I would like to say, of course, it is simple and it is clear that accidental error in position measurements depends on the image processing. I mean, today image processing probably is considered as some toolbox, and we are using this toolbox without changing parameters of this image processing. But I would like to suggest that we can adjust or join image processing to astrometric reduction and join it with the variance of the final, let me say, deviation of stars within the series of images. Finding its minimum will give us the parameters with respect to image processing and perhaps, and of course not perhaps, and also parameters of reduction that we are usually asked for. Of course, I would like to point out that series of images are a good let me say, alternative that does not depend upon the catalog. I have not told anything about astrometric catalog used, and that was not, let me say, accidentally. I mean, this method is independent, and it should bring us to the limits of our instrumental measurements. And of course, I would like to say that the modern algorithms that are used for centroiding, we can do measurements many times of the same image. And we can use the modern, let me say, algorithms for detecting multiplicity of the image. And then we can take for example, the correct way how to treat multiple images. That should improve our, let me say, today astrometry. And also, I have not told anything about photometry, but the problem is quite general. Thank you very much. And I will be glad to answer your questions.
Thank you, Dr. Anatoly Ivantsov, for such interesting presentation. Does anyone have a question or comment? Okay, if not.
May I ask a question?
Yeah.
I would like to ask a question which is not directly connected with the presentation, which I find interesting and nice. But I was a bit surprised with the data which you showed in one of your first tables, and that's that pertains to this very good result of the Naval Observatory in Flagstaff, the code 689, which was achieved in 80s. So do you have any hint how they actually managed to get such a good accuracy? If we know also that after all, also the catalogs, which you didn't mention, were unbiased completely at that time.
Yeah.
Do you have any hint how they managed to achieve such a good accuracy?
Thank you for the question. I was also studying the papers of Ronald Stone, who has been responsible for observations there at Flagstaff, and I've understood from the papers that the telescope used there was 2 meters focal length, so it's quite, let me say, short focal length telescope. But the telescope was studied quite thoroughly. And Stone has introduced into reduction, not by just mathematical fitting, but he introduced through the physical parametrization of this reduction. For example, he has put even sensors for atmospheric parameters measurements and include refraction calculations, not as approximating coefficients, but from the, let me say, refraction calculations that we know from the physical, let me say, representation. And of course, it, as far as refraction is quite a big trouble for all optical observations on ground-based, then reducing this effect or considering it for the specific wavelengths has to improve results. Also, as I've understood from the Stone's papers, is that he used mask for optical distortion correction. And that is also a great, let me say, advance for getting better results. As to me, for today, we need to use optical distortion correction for each measurement, in fact, done for in astronomy, because we are able to get real position measurements. And these effects are no more, I mean, optical distortion are no more small. And also, Flagstaff is located at a good position on the mountain, let me say, on the mountain top. So we can say that atmospheric, let me say, influence is quite reduced. And I can add that if we divide the standard error that Stone has reached at this telescope for observations of asteroids, it is 600 of arcsecond. To the scale in the focal plane of his telescope, we will get the number that is close to 1/10. Let me say, without any dimension, 1/10 of pixel. So we can think that ordinary image processing can reach probably this number, like 1/10. But if we apply some specific methods, there are some papers related that we can go really down to about 300.
Yes, I understand, but it is clear that this kind of very particular effort cannot be applied routinely. Okay, thank you. I understand now.
For the question. Once again, thank you, our presenter. We are late and we have to go to move on the next our presenter. Who is Dr. Zinovi Malkin with his presentation named Comparison and Combination.
Ivana, just quick note from organizers, we cannot hear you very well. Can you come closer to your microphone and speak louder, please?
And now we have to move on to our next speaker, who is Dr. Zinovi Malkin with his presentation, Comparison and Combination of Radio Source Position Catalogs. You can start with your presentation, Dr. Malkin. Do you hear me?
Okay, organizers are taking a conference now until Ivana fixed her microphone. So we are glad to have with us Professor Zinovi Malkin, who will give talk about comparison and combination of radio source position catalogs. Professor Malkin, you are welcome.
Oh, can you hear me?
Yes, you are welcome to start your talk.
Okay. First of all, I would like to say that it is special pleasure to me to participate in this conference because we know very well, a very long time, the Belgrade Observatory is one of the center of the astrometry. And we very well know before that many Belgrade astronomers were close cooperation in our Pulkovo Observatory, such our colleagues Teletis, Adjakov, Michic, Dacic are very well known here. It is great pleasure to visit you, unfortunately, only virtually. Also, I would like to say that ground-based astrometry, especially in Europe, is now not at very good shape after the development in the space-based astrometry. Nevertheless, I think that some experience of the ground-based traditional astrometry can be still useful even in the Gaia era. And for example, technique for comparison and combination of radio source position catalogs may be useful and may be profit for construction of the next ICRF catalogs, independently of radio-based or optical catalogs. So the motivation of this presentation is as follows. We know that history, the most accurate CRF realization is the classical astronomy, namely fundamental catalogs have been obtained by the combination of the individual's catalog coming from different observatories, different studying teams. The primary primary topic in this combination is investigation and accounting for systematic differences between individual catalogs. So the technique of investigation of systematic differences became actual in our cosmic era too. Now I would like to discuss some works made during last 10 or 15 years in Pulkovo, at the Pulkovo Observatory. In these years, two combined catalogs were computed in our observatory. And here I would like to show and discuss some results obtained in these works and some problems and prospects on this work in future. Now let me remind you the main principle of catalog combination. First of all, we represent the systematic differences between two catalogs due to some set of orthogonal function. It may be old-fashioned function like Legendre polynomial, like Fourier polynomial, whilst recently the Usually vectorial spherical function are used, spherical function harmonic are used for this purpose. It does not matter in this consideration. It is important that we have to compute some expansion of the differences in some set of the orthogonal function, then the coefficients b by this function are subject of the least square adjustment, and this set of coefficients b define in fact the system of the catalog or system of the difference between two catalogs. If we compare our catalog, input catalog with ICRF, for example, or with official fundamental system, we can consider this as a system of the input catalog. The process of the combination can be divided in two main steps, two principal steps. The first step is a stochastic improvement of the ICRF. In our case, we are talking about the combination of the Villebay-based catalogs, which are constructed in the IVS analysis centers. First, we compute the systematic difference between input catalogs and the current ICRF we would like to improve. And we found the B coefficient by least square method for each input catalogs. Now we should average the coordinates for sources in the input catalogs. Of course, I mean common sources in input catalogs. These common sources are used to compute the B coefficient or systematic difference of catalogs. Now this coefficients B are applied to the all sources in each input catalogs, and thus it allows us to bring the system of the input catalog to the ICRF system. So we suppose that after this operation, all the input catalogs are brought to the ICRF system. So this catalog that are brought to ICRF system are averaged in turn, and so we can obtain some average catalog CO1. It is designed here CO1, which is considered as a improvement of the ICRF in stochastic sense, which is traditionally for astrometry. Now the second step is to improve this average catalog CO1 systematically. So we compute the systematic improvement of the ICRF in following way. We average all the B coefficients of the individual systems, or in other words, the B coefficients. Important step is to assign the proper weights for each catalogs. In our case, weights varies from 1/3 to 1 in the least square solution. It is no time now to discuss in detail how the weights were assigned. In brief, they were computed by the analysis of the differences between input catalogs and average catalog, which is traditional, but also can hide some problems in sense of systematic accuracy of the average catalog. Now this average, to provide such averaging, it is important that these coefficients B are computed for each catalog to the same boundary G. G is this number of harmonics which are computed. Number of harmonics are computed is a separate task. How to determine the optimal number of the harmonics depending on the decreasing of the reminded errors, demanded error and difference between adjusted catalog and input catalog. So average this coefficient B, we can compute the average system, which can be applied to the catalog CO1. Then we can compute catalog CO2, which is now considered as improvement on the observation in systematic sense. So which catalogs we used as input? First of all, it's catalog available online in the IVS data centers. Like I forgot to mention, IVS and International Web Service for Astrometry and Geodesy and Astrometry, which coordinates of the radio astrometric works during last about 20 years. It was organized in 1999. Some catalogs are not present in the various data centers, but they are available on the institutional websites where they can be taken and used in analysis. Some centers not publish their catalogs neither in AWS nor in the institutional website, so these catalogs can be provided by authors by request. Finally, we used this catalog computed in Australian Center, BKG Germany, CGS Italy, GSF United States, IDG Austria, Observatory Paris, France, Shanghai Observatory in China, and United States Naval Observatory also in the United States. This is example of the systematic difference between input catalogs and ICRF2. Let me remind you that it's a rather old work made in about 5-6 years ago. So the catalogs were compared to ICRF2. So we can see that systematic difference between catalogs are quite different, despite the all analysis center analyze about the same set of observations. Nevertheless, differences analysis options, difference in other approaches used in different analysis teams cause such differences in the systematic errors of catalog. So some differences are very close. For example, this after slash, it is name of the software used for analysis. So most centers use Solve analysis development in the Goddard Space Flight Center, NASA. Some teams use own analysis, such as OCAM in Australia, such as WIFS in Austria. That's all. So we can see that some centers are very close in analysis, option analysis strategy. Others are too close, but between these, but differ of other centers. It is differences in systematic difference in rate ascension. So the same for declination. Also, we can see that the systematic differences are different, generally different for the various analysis center. This makes it reasonable to try to combine this catalog to mitigate the systematic differences in combined solution. So this is a result of computation of the catalog CO1, which means the catalog improved, which is pretend to improve the ICRF2 in our case in stochastic sense, and this catalog CO1 should be the system of ICRF2. We can see the systematic differences in both rate ascension and declination are very few microsecond, which means that our attempt to bring the input catalogs to system of ICRF2 are quite successful. After that, we applied the average system of catalogs, so we can suppose that our catalog CO2 shows systematic differences, systematic errors of ICRF2. We can see that our estimation of systematic differences is at a level of about 20 microseconds. It is quite visible value in our time when we pretend to have the accuracy better than 10 microseconds, which is compatible with accuracy obtained from Gaia observation, expected from Gaia observation by the end of the mission. I would like to say that this result was obtained about 5 years ago, as already said. Now it is considered as underestimated because the latest results show that systematic differences of SRF, systematic errors of SRF2 are about 2 times greater, but it was shown only using the more recent observations which were not used in this work. So there are many problems which will be discussed in brief later. Now I would like to stay on only one point in detail because I have now time to discuss more problems, which this problem is usually not considered in analysis work, but it is very important. Source coordinates based on available solutions are computed in least square solution. This least square solution, as we know, includes full solution covariance matrix. This covariance matrix is usually not used in fuzzy analysis, which is not very well. It should be investigated what we lost in our results if we don't use full covariance matrix. Unfortunately, the Gaia CRF lacks the full covariance matrix in principle. Nevertheless, we can investigate this impact in Wilby-based solution. First group that showed this problem was a group in GPL headed by Chris Jacobs. They showed that using the full covariance matrix cause a large difference in orientation angles between catalogs with respect to the case where we don't use correlation between sources at all. Однако we should note that full covariance matrix is usually not published by authors of the catalogs. Instead, the only intra-source correlation are published, namely the correlation between right assertion and declination for the one source. For each source, the one correlation is published between right assertion and declination for this solution. This was investigated further by Sokolova and Malkin several years after that. And so this our final result that if we compare two catalogs, unfortunately only two catalogs were available with accompanied by the full covariance matrix. Only catalog computed in Goddard Space Flight Center, NASA, and catalogs computed in Technology University of Wien in Austria. So we can see if we use only diagonal matrix, namely only errors of imposition without any combination or without any correlation, we have this forward orientation angles between these two catalogs. If we use two diagonal matrix means that we use intra-source correlations. Sorry?
5 minutes more you have.
I can 10 minutes. I started 20 minutes ago. Okay. Okay, thank you. Okay, two diagonal matrix means that we account for the correlation in each source between the right assertion and declination. We can see that angular orientation angles are practically the same. The difference is very small. Однако, if we use full covariance matrix, we can see the orientation angles differ very substantially. It was substantially in absolute sense, more than 20 microsecond in A1, and this difference is very statistically substantial. So, which other problems we can see when we work on combining of the comparison of the VLBI-based catalogs? First, it is important correlation on the data set. Unlike the classic optical astrometry, all the analysis center process the same data set collected by the same VLBI network, EVS VLBI network. So this is main problem, which many people think that there's no sense to compute the correlation, compute the combined catalog from VLBI input. So the result is depends on the source set used. We can use common sources or common sources. We can use only core or defining sources from the catalog or other set of sources selected from some criteria. Very important point is handling of outlier. Result depend on how we detect and reject outlier. A classical problem in the coming still from the optical astrometry is how to properly weight the catalogs. Another problem are practical problems. Currently, there are very few new input catalogs. The 8 input catalogs we used 5 years ago are not mostly available now. Most of analysis center now don't publish their catalog or publish their catalog very old, which are dated 1 or 2 years ago. And so analysis center should be encouraged to do it more frequently. Absence and complete covariance information. Authors of the catalogs don't publish generally the full covariance matrix. So to summarize, I can say that method of compute the CRF only combining catalogs based on modified classical astronomical approach is realized at intensity at Pulkovo Observatory. In further developments are underway now. CRF only combining catalogs can have advantage over the combining CRF Europe solution because of accounting of full systematics. I would like to say that CRF Europe solution means that single very big global solution allows us to compute simultaneously the celestial, terrestrial, source coordinates or celestial reference frame, station coordinates or terrestrial reference frame, and Earth orientation parameters. Moreover, VLBI, being one of the space geodesy techniques, can be combined with other space geodetic techniques such as GNSS, laser ranging of satellites laser ranging, lunar laser ranging, and so on. These satellite techniques also define the station coordinates, also define the Earth orientation parameters. And some groups, primarily the AERS, working on such global multi-technique solution, which which may be not very optimal because this global combining solution, multi-technique combining solution, does allow us to account for full systematics on each technique. And finally, I would like to mention that it's very important to bring in practice to impact to allow for correlation among source position in the input catalogs. And so all the authors of the catalogs are encouraged to publish their full covariance matrix, most optimally publishing their catalog in SINX format. No, there are some publication of our results. There are three main papers that are available from me on request. And finally, thank you for your attention to this work.
Okay, thank you, Dr. Malkin, for your interesting presentation. Now we have time for questions or for comments. Does anyone have a question or comment, please? Okay, if not, I want to thank once again to our presenter, Dr. Malkin. Now we have to move on to our next presenter, who is Miljana Jovanovic, our colleague from the Astronomical Observatory Belgrade. With her presentation, control stars around quasars suitable for the ICRF to Gaia CRF link. Miljana, the floor is yours.
Hello. The subject of this presentation is related to my PhD thesis, linking Gaia Celestial Reference Frame and International Celestial Reference Frame and R and V magnitudes of selected quasars. My supervisor is Dr. Goran Damjanovic. We use F-test to analyze photometry of control stars, which we selected for differential photometry of objects, which are important for the dimensional link. Here will be presented results of these statistics. And for a few very, the most observed objects, this is 5 objects. They are mostly active galactic nuclei. And the time scale variability of AGNs is divided in 3 classes. Those less than a day are intraday, with a range of few days to few months, and short term from few months to several years, and long-term variabilities from several years. There are several papers about connection between brightness variability and astrometric positions. Because of that, it is necessary to monitor the brightness variability over a longer period of time. In this table are listed properties of 5 objects, their names, coordinates, redshift from net catalog, type from SIMBAT database. Observational period was about 6 years. Most observed object was 1741 plus 597 in R filter. Some results from this period of monitoring were presented on several conferences and papers. I mentioned here only a few ones, the new papers, and you can see references later. Observations were performed using 8 telescopes. 2 telescopes are located at Astronomical Station Videvica of Astronomical Observatory of Belgrade in Serbia. One of Gassegrain type has mirror diameter of 6 centimeter. This is ASV 6 centimeters telescope, and its picture you can see in figure 1. Second, Ricci Critian has mirror diameter of 1.4 meter. In figure 2, you can see telescope, dome of telescope, and telescope inside it. The third one is also Ricci Critian, 8 centimeters telescope, which is located at the observatory in Montsec, Spain. It is Juan Ro telescope, and most of the data were performed using these 3 telescopes. Also, we used 3 telescopes located at Rozhen National Observatory, 2 meters, 60 centimeters, and 70 centimeters Smith camera. At Beograđic Observatory, also 60 centimeter Ricci Critian telescope, and a Leopold Figel telescope, which is located at observatory at Vienna, Austria. It is 1.5 meter Ricci Critian telescope. In table 2, you can see telescopes and cameras and properties of these cameras which is mounted on the telescopes. And it is interesting that Apogee Alta 42 was mounted on 2 telescopes at Astronomical Station Videvica. And as big as the 10 was mounted also at, it is a camera with the same type at Astronomical Station Videvica and Leopold Figel telescope. And under Icon L was a camera with the same type was mounted at astronomical station with it's a 1.4 meter, and Rosen, and also TJO telescope. So it is interesting that this data was compared, and some of this data was used for comparison of photometric results, and these results were presented, some of these results were presented last year at 8th Sub-Regional European Astronomical Committee Conference and published in Bulgarian Astronomical Journal. With a different type of camera, mounted on different type of telescope, we have a different type of field of view. It was very interesting, and we had to our data to be performed, and we need to use stars which are very, very close to the objects. Usually, we two CCD images were obtained per VLR filter, but sometimes we use B and I filter, depends on time of observations, and in some period of observations we have B, V, R, and I filters also obtained. Every night we obtained also bias dark and flat frames for data reduction, and reduction was performed using advanced image calibration with IRF scripting language. Images were corrected for hot and dead pixel and cosmic ray. Hot pixel map was obtained using dark frames, and dead using flat frames, and cosmic ray map was obtained using Lacosmic from Peter van Dokkum. Object brightness was determined by using differential photometry. Brightness of object was calculated for known brightness of its comparison star in Maxim DL software, and stars were chosen from 14 data realization of SDSS catalog, except for object 1722 plus 119. Stars were chosen from the Doroshenko et al. 2014. All stars were chosen not to be variable, not to be far from object, not too bright or too faint, not very blue or red stars, and etc. From selected stars, we chosen 2 comparison ones, and the rest were control stars. And this is mostly for data from 2016 and for data from telescope TJO. Before that, we use more comparison stars. We didn't have control stars, but now both data are now merged and will be presented here. For transformation from SDSS magnitudes to Johnson-Carson magnitudes, we're using equations from Honis-Gaskill from 2008, and here are equations for V and R transformation, and these equations are restricted to be valid for this criteria, so which also was one more criteria for selecting stars. In figure 4, you can see charts of the field of these objects, and objects are presented with circle and number 1, and stars with other numbers, except for these objects 1732 plus 119. The object is presented with lines, and the rest are control and comparison stars from Doroshenko et al. Object is number 1, and most of the stars are around this object. So we choose the best what we could to be with the same or similar brightness as object and color. And here you can see results of photometry. In table 3, it is coordinates for comparison and control stars of objects, and the V and R magnitude, which was transformation magnitude from SDSS to V and R band. And in table 4, you can see average magnitudes for this period of observations from July 2013 to August 2019. And data are similar, or the results what we obtained is in line with the input magnitude for differential photometry, and agree with errors of transformations and standard deviations what was obtained from this period of observations for control stars and also for comparison stars. Control stars are A and B, the rest are comparison stars. And you can see it is very similar no matter what the color of the stars is. Our analysis method we use, first we apply 3 sigma rule to exclude some and reject some data. Then after implementing Shapiro-Wilk test, we concluded that we could perform F-test, F-statistics for to compare brightness of stars with we compare comparison stars brightness and control stars brightness. And F-test is a little modification. It is modification of F-test. We compare differences of magnitudes. Comparison stars magnitude is S, and comparison magnitudes stars A and B.
You have
we
5
have
more. 5
thank you. These are 3 hypotheses, and we compare with the brightness of one stars and differences of brightness of control stars, and hypotheses are discarded if F statistics are greater than critical value for significance level of 0.001. And these are results. And for objects, F statistics are greater than critical values. But for stars are less than critical value, except for some cases. And most of comparison and control stars are useful for differential photometry. We could say that from our results. We will investigate F-test results where it is greater F statistic than critical value, and decide if we need to repeat differential photometry of objects, and we'll see when it is necessary. And we will continue with the observations to perform more data, and then we could decide better what is the best for continuing investigation of brightness of comparison and control stars, but for objects, what is very important. And here is references, the main and the newest one, and this is references of proceedings publication, papers which are published in Proceedings, and also in other papers where we presented results, our results from these 6 years, some from the 3 years, and some before 2016, where it is comparison with our data with Gaia Celestial Reference Frame data. And thank you for your attention.
Okay, thank you, Milena, for this interesting presentation. Now I open the floor for question or for comments. Does anyone have a question? Or comments? Okay, if not, I want to once again thanks to our speaker, Milena Jovanovic, and we have to move on to our next and the last speaker, Dr. Milan Stojanovic from the Astronomical Observatory Belgrade, with a presentation, Solar Neighborhood Kinematics based on the Gaia data.
Good morning.
Milan, do you hear me?
Yes, can you hear me?
Okay. Now you can proceed with your presentation.
Thank you. Okay, good morning one more time. I will talk about actually the use of Gaia data in the research that I was working on after my PhD. So this is what I will present here, just one part of work in progress of one bigger paper that should be published soon. And here are the co-authors, the colleagues that I'm working with: Rafael Kubasi, Zorica Cvetkovic, Rade Pavlovic, and Slobodan Vinkovic. So you heard a lot about Gaia, and I just wanted to tell you all one more time that this satellite was launched in 2013, and what is the most important new information about Gaia is that it got the extension for the mission to last for now 1.5 more years after the 5 years of nominal operations. So what we have done is that we first wanted to choose the sample that will be later used. We chose all stars from Gaia that have these characteristics. So first, we wanted to look only for the stars that are in solar neighborhood, in our solar neighborhood right now at this moment of the observation. So we chose all the stars with parallax smaller than 100 parsec. Then we wanted to see to take only the stars that have proper motion, position, and radial velocity. And you probably know that biggest number of these 1.7 billion stars in the Gaia catalog, they all have proper motion positions, of course. For the parallax, it's around 1.3 billion, but when we come to the radial velocities, then it's a much smaller number. So in total of 7 million stars with radial velocities, we have chosen 74,339 stars that are closer than 100 parsec and that have this necessary information for mainly for calculating galactocentric orbits, which I was working on. So you know that there are some problems with when you choose a sample, and if you want to have a good representative sample, then you need to avoid the possible problems. And if you go on a website of Gaia. Current data release 2 has these known issues, and you can find it here on this link. So there are some astrometry issues. There are some problems with estimation of uncertainties and other things. But what is probably the thing that mostly influenced our work was this problem with the radial velocity. So they know that they have at this moment problems with the calculation of proper radial velocity when the star is in crowded region where it can happen that the spectra overlaps, so from the neighboring stars. And they shown this problem in details in this paper. Here on the left side, you can see how it looks when two stars very near. These are Gaia. There are designations of the Gaia stars here, so in the Gaia catalog. And if they are close one to another, then you can have a possible problem with the radial velocity. But this is not the only problem. There are other problems. For example, when number of transits is smaller than 3, then you can have again possibly wrong radial velocities. There are some other problems that Bobert and his colleagues discussed in details and presented in this paper recently in the last year. This is how it looks. So this is 7.2 million of stars with measured radial velocities. This is the number of stars, which is very big, which is 1 million, that have a number of transits smaller than 3. And they say that with the DR3 and possibly DR4 or the final release of Gaia, of course, this number will be much, much smaller because they will have more measurements for each star. This is the number of stars that are found in these crowded regions, 70,000, and they published in this paper the list of all these 70,000 stars, so you can easily remove them if you are doing some research. And this is finally a clean sample of radial velocities that consists of 6 million stars, 6.1, and this is how it looks. So what we have done, we started with this 74,000 stars, and then we removed in total 9,891 stars from our sample because they were affected with, by one of these problems. The next thing that we wanted to do before the part where I was working on, which is a calculation of galactocentric orbits, and then we wanted to see which star belongs to which component of the Milky Way galaxy. Mainly, we wanted to distinguish stars from the disk because that is, let's say, of the biggest importance for the work that we are currently working on. So when you want to see or to calculate the galactocentric orbit, of course, these parameters that I mentioned, like proper motion, radial velocity, parallax, they're all very important, but you can have big problem if you are trying to make the galactocentric orbit, like one presented here, of the binary star, because binary stars, they have their own motion around the center of the mass, and the measurements that are coming from binary stars are usually not so reliable and can be problematic if you want to do something like this. On this graph, this is a graph from Washington double star catalog. You can see how the number of confirmed systems, binary systems in our galaxy is growing as people are more and more researching the double stars. And currently in this catalog there is around 400,000 of stars that are in this catalog. So we made a simple correlation. We wanted to find all the stars that are in this VDS, Washington Double Star Catalog, and to investigate these stars and potentially to remove them from our sample of stars. We found in total 3,269 stars from VDS in our sample of 75,000, and we removed around 1,850 stars. I want to show you one example. This is example of DUN 23. This is a designation from the VDS. This is a double star. It's a confirmed binary, so it's not an optical pair. It's a confirmed binary, and we got two completely different heliocentric orbits. Here you can see one classical boxy orbit representing the disk star, which is without any doubts. But on the right side, you have a orbit of definitely a star that could be a thick disk or thin disk, and you see these arches. So this is a star, for example, that we want to exclude from our sample because we cannot say that this star has a properly defined RP and RA and eccentricity and so on and so on. So what I wanted to show with this example is that a binary star cannot have something like this. So if a galactocentric orbit of one star from the binary system looks like this, the other star should have the same orbit. The problem that we have orbits like this is coming from the just from the data that Gaia could not measure properly because of the motion of these two stars. So you can have usually, and in this case also, the problem was radial velocity for both components. It was not measured properly, and then you can have things like this. So we removed these stars also. We investigated each one of them separately, each pair, and we saw that there are examples like this, but in most cases, the motion of these stars were, let's say, the data was good. So in most cases, we get the same orbit for both stars from the system. We used some new criteria for segregation for disk and for halo, and the rest of the stars were disk stars. In total, our final sample had 62,598 stars, and a thin disk for this solar neighborhood for stars around 100 parsec around the sun. You get this value that was expected, and there is only 1.3% of the stars that were, let's say, caught in this sample that belong to the halo. So others are thin disk and thick disk stars, and that's the part from the work that we are currently doing that I wanted to present here. And as I said, this is a work in progress, so these are preliminary results, and we will publish all this in a new paper when it's finished. Thank you all for your attention, and if you have some questions about this, I will gladly answer.
Okay. Okay, thank you, Milan, for this such interesting presentation. Now we have a lot of time for question or for comments. Does anyone have some question or some comment? Okay, if not, I can close this morning session.